Καλημέρα. Θέλω να ευχαριστήσω τους διοργανωτές που με καλέσανε και επίσης για τον Πέτρο για αυτή την πολύ ωραία ομιλία. Συνεχίζω στα αγγλικά. I'm saying I'd like to thank Petros for the vision. I have a much simpler task because I'm presenting some things that in machine learning are called classical, which means more than 3 or 4 weeks old. But I was reminded in seeing Petros's talk and recognizing that he is at once a physicist, mathematician, AI researcher, and I remembered an old story, which maybe some of you have heard, about Niels Bohr. So if you haven't heard it, let me indulge me and let me tell you. So Niels Bohr had a visitor once, and the visitor came to his house and he remarked that Niels had a horseshoe that was above his door. Now, they say that that putting a horseshoe above your door brings good luck. And so the visitor says, Niels, what is this? This is some superstitious nonsense. You're a man of science. Don't tell me that you really believe this, that this brings good luck. And Niels looks at him and says, no, of course I don't believe it, but I'm told that it brings good luck whether you believe it or not. So when I see the quote by Ilya, I can't help but think about that. Okay, so we are going to, I guess, move very, very closely into the mountain that we were on the side of before, and look at some very, very specific details about really what is a classical problem in machine learning. So this is in no way related. I'm not going to present any of my own research results. I guess I should start by introducing myself. I'm a professor at the University of Texas at Austin, and I'm also a researcher at Archimedes AI, which is here in Athens. So let's start from sort of the beginning of the story. And I want to say that whether or not we think about doing machine learning as supervised learning is an underpinning part of machine learning because it provides us the central computational tool, whether you're doing generative AI or whatever it is that you are trying to solve. And the basic problem in supervised learning is from examples X and Y. I want to learn how to predict Y when I'm given X. Okay, so for the computer vision experts in the audience, do you know what this is? Do you know why you should know what this is? Because this is the very first category from ImageNet. So this is called a tinka tinka, I guess, also a doctorfish. So this is an example of that we're all familiar with. I get an image X and I want to predict Y. Another example of learning from data. So here's a quote from Zor Sari, who is an author, a famous Greek author. It says, «Τη διάρκεια του πολέμου η Ζορ Σάρι συμμετείχε στην αντίσταση, περιγράφοντας εκείνα τα χρόνια, η ίδια λέει, τα χρόνια της κατοχής ήτανε χρόνια». Okay, so the brilliance of NLP and these large language models is that they've harnessed a huge resource, basically the entire internet, everything that's available, and created from there supervised learning problems. So in this example, X would be this first paragraph, and Y would be that hidden word. By the way, does anybody know what she actually said? It is one of these. Would you like to guess? And it's not, I'll give you a hint, it's not Peponiou. Hey, actually, she said charas. You need to read the full quote to put it into context, but it is surprising. Okay, so my point here is that creating supervised learning problems is really at the computational heart of the machine learning pipeline, regardless of the application, regardless of the type of system that you are building. And so there are regression problems from computer vision, from natural language processing, whatever you like, Another classical problem is density estimation. So I think those three, regression type problems, classification problems, density estimation problems, form three of the main pillars of things that we want to estimate in one, or learn in one form of another. And much of what you'll hear today is illustrating all of the amazing things that can be done. So this talk is really about what are the mathematical underpinnings of this? What are the questions that we are actually asking when we try to see when can we learn something? So here's a very simple example. I have these blue triangles and red circles, and I need to learn how to predict I need to learn from this, and we should be careful about what we mean. You know, what is it exactly that we are trying to learn? So that's the first basic question. Are we trying to learn exactly the form of that separating line, or are we trying to learn exactly how to predict, for example, the next point, this black circle? And there's a significant distinction between those two things. And there are some things that obviously we can't learn. So what is this example? X, just like in the previous example, are the coordinates. So imagine I give you an I and a j, and I show you some fraction of these. There's 400 squares in this picture. I show you some fraction of them, and then I give you new coordinates, and I ask you to tell me, is it blue or red? So obviously here there's nothing, we need to see everything in order to be able, all we can do is memorize this pattern, whereas this is an example of something very similar. I show you I and j coordinates, and you need to tell me blue or red. And so very similar examples. One is clearly possible, just at an intuitive level so far, and one is clearly not possible. So what I'm trying to motivate is we actually need to understand, in addition to using these amazing tools that are able to solve this tremendously broad suite of problems, and it's also important to ask that first question of why is it? What is the difference between this problem and this problem, and what is the mathematical basis for that? And I think this is especially important for the students in the audience that are looking for different directions of research. Some are more applied, some are on the more theoretical side, and I think that there are the really fundamental questions open that remain. Okay, so the basic principle, and that has laid the framework or foundation for the success of machine learning, has been this idea of risk minimization. Okay, so what is this? So we're given, again, data, and the basic assumption is that the data are drawn IID, and future data are also drawn from this distribution. It's important to say that, not because we're asserting that that is how the world works, but because we assert certain principles to form our understanding, and then when we see observations or we see that something deviates from that, we go back and we can reevaluate what our assumptions are. But the classical assumptions are these. So let's keep these for the moment. And the risk minimization problem is, there's a lot of notation, but I'll try to help you so you don't have to keep too many things in mind. I'm trying to learn this parameter theta. And for different values of theta, I do better or I do worse in my prediction. So this is an expected loss. So theta, for example, could be the line. The line which says if you're on the top right of that line, you're a blue triangle, and on the bottom, you're a red circle, or whatever it was. And or we can think of this as theta as being the weights of a neural network. Okay, so in this simple example, this is how I would parameterize this theta, and my loss function would just say be 0 if you got the right answer, and 1 if you got the wrong answer. These are my choice. I get to choose these things. And so this is the problem that I want to solve. But what is the problem? I only have data. I don't have this expectation. I don't have the distribution of images. I don't have the distribution of next words. I don't have the distribution of the next patient that comes into my office or takes an MRI. So the basic problem that statistical machine learning tries to address is how well can we do when we have finite pieces of data, and yet I want to solve this problem. So if someone asked you and you had never seen this before, I think we would all say the same thing. Well, let's just approximate this expectation with finite samples, the same way we approximate an integral, everything that, and what else could we really do? And this indeed is what we do. This is called empirical risk minimization. When we train a neural network, we have data, we try to find parameters that agree with those data. That's basically the story. So one option, or one really important direction, and I think most of the talks that you'll see in the next days focus on the amazing things that you can accomplish following some version of this paradigm. But I'm interested here in a more specific question, which is, when does this work? What conditions? What kind of conditions do we need? Okay, so in other words, I have these top two lines. Theta star is the optimal solution if I had all of the data in the world, all past, future data, if I knew the distribution exactly. And theta n is the best that I can do with just my finite data. And so the central question, of empirical risk minimization, of statistical machine learning, is, first of all, consistency. Is this ever going to work? And what do we need for this to work? And so consistency means, what is R of theta n? This says, I took my finite data, I did my best to estimate theta n, which is going to be through some optimization, which Stasios is going to tell us about in the next hour. And I computed the risk, the loss. And I want to know, does that give me any bearing on how well I might do, or an optimal solution might do? And then that's the qualitative aspect of consistency. Then the quantitative aspect is to understand, okay, if I have 100 samples, how well do I do? Or actually, even more importantly, if I double the number of samples I have, how much better will I do? That is the actual question of the rate of learning. So, for example, in classical theory for regression, we know that if we want to cut our accuracy, we want to double our accuracy, cut our error in half, we need to quadruple the number of data points. So these are the kind of quantitative statements that are interesting and that are important. So I want to talk a little bit about where do these come from and what do we need in order to get them. So when can we guarantee consistency, and how can we control sample complexity? And in particular, how can we design algorithms that have these two properties? Okay, so there's a fundamental theorem of statistical machine learning which says that these two things on the left and the right are close, they converge, if and only if we have this uniform convergence property. So this is a technical overview, so I see that I'm kind of speeding through, but I think it's important to understand and appreciate what are the actual problems that we want to solve. So let me just parse through what this fundamental theorem says. Okay, so what I'm interested in is, if I get data and I solve on the risk minimization problem, I find the parameters that fit those finite data as well as possible, when is that going to tell me something about my general performance? And this theorem says something that shouldn't be that surprising given that that's our goal. And it says that my finite data problem will tell me something about the full data problem if and only if, so this is a necessary and sufficient condition, if I have this uniform convergence. And it's called uniform convergence because you see that the supremum is inside the probability. If I took it outside the probability, it would be a very much weaker statement. Okay, so what does this statement say? It says that I look at R of theta, the risk of any given parameter, and I compare it to what I estimate the loss to be given only my finite data. So in other words, I take a neural network with fixed weights, frozen weights, that's theta, and I want to know how well did that neural network do on my n data points. That's the right, that's Rn of theta. That's what I have, I can compute that number, and I really want to know how close is that to how well, on average, my neural network would do on all of the data that I will ever get. That's R of theta. And I need to make sure that this number is small as n gets big, but it needs to be simultaneously small for every possible setting of the weights of the neural network. Okay, so this is what uniform convergence means. We can argue about it, but actually we can't really argue about it, because this is what this fundamental theorem says, that this will only work, that ERM, this idea of doing anything on a finite amount of data, is only a principled idea if this limit goes to 0 with the supremum inside, if you have uniform convergence. So the question of whether or not ERM is going to work basically comes down to when can we guarantee uniform convergence. So let's see a concrete example, so maybe this will help fix ideas. Okay, there's a very simple example. X comes from a uniform distribution between 0 and 1, and if it's in the first half, if X is in the first half, the label is 1. If it's in the second half, the label is 0. So if you took a machine learning class, probably the very first algorithm that you learned is the algorithm on the left. This is just a decision tree. So sometimes I like explaining things in Python. And so this is just the Python command for all of the possible f of x theta on the left. And on the right, I just didn't specify the max depth. So on the right, exactly that theta this is the same as fitting a decision tree of arbitrary depth. Okay, so I think probably everyone has tried to fit a decision tree classifier on data. So my question is, okay, for uniform convergence, what can we say about the things on the left and the right? So does anybody know on the left what kind of convergence would I expect? Yeah, so I want this to be small. So, the model, yeah. So what we're saying is that x is drawn uniformly between 0 and 1, and then y is deterministic. So the conditional, is the question about the model?
Can you repeat please the question again, because I...
Yeah, so this is
Yeah, it's... Mm-hmm.
Okay, so the model is that x is drawn uniformly between 0 and 1.
Mm-hmm. Yeah.
And once x is drawn, y is deterministic. If x is in the first half, the label is 1. If x is in the second half, the model is 0. And I want to know if now I'm looking at this type of classifier on the left, where I've written example 1. So what does example 1 do? It's parametrized by a single parameter, alpha. And so capital theta contains all of the sets between 0 and alpha. So I get to change alpha. I'm looking for a particular alpha, and I will do that to fit my training data. And for a particular choice of alpha, I have my classifier f, and what does f do? It looks at x, and if it's less than the alpha I chose, it says 1. And if it's bigger than the alpha I chose, it says 0. And I want to know how quickly does that converge to basically the truth. Another way to say it is, for a particular choice of alpha, you see how many mistakes you made. Mm-hmm. And then for that same choice of alpha, you see how many mistakes would you make in expectation once you get all infinite future data. And I'm asking, how do those differ? I want that eventually to go to 0.
You mean have like 0 probability? You mean, like?
Well, they're going to have more probability.
More probability.
Yeah, they'll have. Okay, so maybe I'll tell you the answer. So you can check this as an exercise. This will scale an expectation as 1 over n.
Well, this, I think this is maybe a serious problem. You know, it's when we talk about mathematics, it's when we have finite or infinite series. If it's the series converges to 0 or 1, so it's in its value. If its value is diminishing to and then to converge to 0. If it's 0, it's the to minimize the risk of make maybe a fault guess.
Maybe it'll help if I just explain.
It's how to reduce the probability of something to make a fault guess. It's when you have you know, some elements of x and you have to predict y, for example.
Yes, this is my problem. Yeah. So let's see why it is 1 over n. So if I give you if I give you n samples, but uniformly distributed between 0 and 1, what is your choice of alpha going to be? If you want to explain your data perfectly, it will be the maximum sample that you got that's less than 1/2. Right? That's what will get you 100% accuracy.
Okay.
I'll dwell even more because the rest of the I think the 3 days will be different. So it's worth thinking this through to understand. Right? So you get 100 samples. What would you do? What is the optimal theta going to be? It's some interval between 0 and 1. And I want to know what is the difference. Essentially, another way to say it is what is the difference between the empirical mass and the true mass of that interval. And you can see that it will basically scale like 1 over n. I'm not sure I understand the question. Okay, we just keep going. Okay. What about the thing on the right? So the thing on the right, you can also convince yourself easily that there is a set of intervals which covers all the points that you care about. So it has 100% accuracy on the data, on the training data, but essentially 0 accuracy on the full data. Okay, so these look very similar. They look very similar in the syntax that we use to define them. They look very similar mathematically, but obviously this thing on the right is more complicated. So our first intuition is that we need, if we want to have this uniform convergence, we need this theta to be not too large. And this is a first idea. Okay, so let's try to make this a little bit more precise. And so here's a little warm-up thought. So suppose I have the 0-1 loss, and I want to know what is this difference. This is for one single theta. I'm fixing this one theta hat. And I want to know what is the difference between the error that I estimate using finite data or the error that I would estimate using infinite data. This is the basic question. When is this bigger than epsilon? So let's write this out. So this is the first term is the probability that the expectation, I guess I should be close to the mic. This is the probability that the expectation, I'm sorry, I switched the finite and the infinite sample. The first term is the expectation, and the second term is the finite data. And if I bring the expectation inside the sum, then you can see that all I'm really asking about is when is a sum of 0, 1 IID random variables close to their mean. That's all that this question is. And I have tools for that, so that we know that this converges like e to the minus n times epsilon squared. And there's many different ways that we can see this, but it's basically an application of Hoeffding's inequality. So again, for those of you that are, it's hard for me to gauge from the audience, but for those of you that are interested in the mathematical foundations of statistics and probability, concentration inequalities are a fundamental tool, especially for obtaining these kind of finite sample quantitative guarantees. Okay, so we know this. If we have just one theta, then this thing converges like e to the minus. Okay, ευχαριστώ. Τέλεια. Αυτό βοηθάει. Όχι, δεν πειράζει. Μένω εδώ κοντά στο μικρόφωνο. And so, I guess I can also use the mouse. Right, so we know that this is we have this answer just from Hoeffding's inequality. And if I don't have just one potential set of weights for my neural network, there might be 2 or more, then I can just use the union bound, and this 2 comes down. And if I have m possible thetas, then I have something like this, just by the union bound. So how, is this a good approach? Is this going to work? Can I just keep using the union bound? When is this a good idea? So when is this going to be small? Well, I have one term that grows and one term that gets smaller. So how small does m have to be in order for this to give me a favorable trade-off? It should be smaller than log n. So this analysis is pretty good as long as m is small. But actually, even better than that, you can see that as long as everything is close to one of these small number of points, then this thing on the right will make sense, meaning that it will go to 0. Okay, so this is a basic, very natural, very easy to understand condition for uniform convergence. Let me just say again what we're trying to do. R hat is my error on the finite data that I have. So I've trained my neural network. I look and I have 95% accuracy. What is going to be the accuracy when I deploy the model? That's the thing on the right. And I want those things to be close. Whatever the accuracy is, I just don't want to be wildly off. If I've built something that's 75% accurate and 75% is good for my application, then I don't need it to be 100. I just need to make sure that when I deploy it, it's not 40% accurate. I want it to be very, very close to the accuracy that I've estimated. Okay, so this is our question. When does that hold? And this very, very simple statement says that if you're only testing 5 or 10 or 100 or m different neural networks, if that's the only thing that existed in the world, then I would have this kind of uniform convergence. And in fact, what this little picture is saying is that as long as every possible parameter is close to one of these small numbers, then again, I would have this uniform convergence. Okay, so here's the first basic and very classical result that says if you're given n samples that come from some distribution, consider all possible vectors, this entire set for all possible values of theta that you have. Okay, so this could be infinitely many vectors. Sn, I should have written here for all theta. So this is, Sn is a potentially infinite set of vectors. Just like this circle might contain an infinite set of points, but they're all close to this finite number of points. So what I'm going to do is, I have this infinite set of points. I want to see how many cells do I need to cover them so that they're all close to something. So this is called a covering. Okay, so H is called the covering number, and I want to know how many of those do I need. So H is the log covering number. And the basic theorem says that ERM is consistent as long as this limit goes to 0. Now, for those of you that are tracking, you'll see that I just rewrote this exact statement here on the bottom. As long as everything is close to m things, and m scales slower than log n, then this is going to go to 0 on the right. This is exactly what this is saying. You should think about this as being log m here. As long as log m is small, so much smaller than n, then this goes to 0. So we write theorem, but really this is an observation based on just a simple thought process that we had before. Okay, but bit by bit, we're building something that hopefully will be useful. Okay, so what have we not said? So I talked about this is the expected log covering number. Something very similar is the worst case covering number, which is, I guess it's called the growth function. I'll give you some jargon in case you come across it. So this growth function is the worst case log covering number over all possible training data that you might have. So it's not an expectation over these data, it's the worst case. And so if we can control this growth function and not just the log covering number, this worst case, we also get a rate. And it also tells me how quickly I can learn. If I double the amount of data points that I have, how much does my accuracy increase? Okay, so there's a very interesting, well, you might ask, where does this come from? Where does this kind of result come from? Why is it that this growth function doesn't give me something in between? It gives me exactly this kind of convergence as long as you have this. And this is a result that's probably about 40 years old and proved by several different people. So it first appeared as a proof by Sauer and Schella, and sometimes it's called Sauer's lemma. And then it was reproved in a very similar form by Vapnik and Chervonenkis, and probably those are the names that everyone has heard of because you've heard of this term VC dimension. But these are the founders of statistical machine learning. And this is the key lemma that basically gives us this result, and it says that this growth function is either linear, it starts growing linearly, and then at some point it stops growing linearly, and it grows not just sublinearly but logarithmically. And this is the basic important result, and why we get the result on the previous page. Again, if you put these together, you'll see that it follows quite quickly. Okay, so I've told you a number of quite technical details, but well, let's see now what is the impact of all of this on modern ML. So some of you are interested in math and you're interested in theory of probability, and so maybe you're inherently interested in questions like this. But I also want to ask, what does this have to do with the tremendous success that we've seen, and what are researchers that are interested in questions like this, maybe not this exact thing, but are interested in statistical machine learning, what are the interesting questions that are left while that are going on in parallel with all of the application progress that's been made. So the first thing that I said is that this idea of empirical risk minimization is important. It's the key computational paradigm of machine learning, and it's our key computational tool. Controlling overfitting is also the main thing that we want to do. So you've heard of the word overfitting, and this is basically, in the language that I've been talking about today, this is the failure of this uniform convergence. So we overfit, as an example, when we have that unbounded depth tree. When we overfit, when we have a scenario where my parametric class is so rich that I fail to have this uniform convergence. And this idea has led to the development of algorithmic methods, of analysis methods, and let me mention a few of these ideas. And of course, many attempts to understand and explain generalization of neural networks. So this is our first story. So things work. We don't overfit as long as this thing is small. Okay, so what can we do if we do overfit? Well, one idea is let's just make it smaller. Let's have a shallower tree. Let's have a neural network that doesn't have as many parameters. This is one thing that we can do. So, but another idea that again comes out of this thinking, and this is again something that I'm sure everybody who's trained a neural network, you use some kind of weight decay, or you're using something. You're using dropout. You're using something that is either directly or indirectly regularizing. So what does this say? It says that I want to minimize the risk, but I'm also going to give you something else that's not related to the data to worry about. I'm going to add something that you need to balance. Okay, so the original explanation by Vapnik and Chervonenkis said that, well, by adding this penalty, also just by duality of convex optimization, you can think about this as a constrained minimization problem as opposed to a penalized regularization problem, as a penalized optimization problem. So Vapnis and Chervonenkis say that, well, when I add this, this is basically making, implicitly making theta smaller. So theta might be huge, but once I add this penalty, my optimization is not going to consider all these other points. And so if I don't need to consider, if my optimization is not going to consider all these other points, that's as though theta is smaller. And what happens if theta is smaller? The growth function is smaller, the packing numbers are smaller, and maybe that way I can guarantee uniform convergence. Okay, so what is my point here? My point is that I've spent 40 minutes telling you about these kind of very classical results, but regularization is a tool that we use all the time, and part of the motivation of that was exactly to make the effective theta smaller. There was another paper about 20 years after Vapnik and Chervonenkis by Busquin and Lisev that studied the same problem of uniform convergence in a very different way. And they said, I'm not going to worry about how big theta is. I want a different way to prove uniform convergence. And they used stability arguments, something called uniform stability of the algorithm, or algorithmic stability. This is a really foundational paper. I think it's 2002. But again, it is using different thought to explain the basic conditions that we need for empirical risk to converge to true risk, for this uniform convergence. What are some other, even more modern ideas? And I think maybe this is one of the most important ones, is that maybe theta is smaller than it looks. Okay? Maybe because of real-world data, they fill a tiny portion of the space, and because of that, whenever you solve this optimization problem, you're not going to get a theta out here. Not because you disallow it, not because I cut it off, not because I regularized, but just because my data doesn't take me there. So perhaps this is a theme that we'll hear about later today, but there's been a huge focus in neural networks of thinking about what algorithms are we going to use. What is the architecture? What is the new architecture that we're going to use? How much training do we need? But I think increasingly one of the most fascinating stories is this idea of what is the data set that we're going to use? And changing the data set can dramatically change what the outcome is. Now, I think we're at the stage where it's most important to score successes in that area and see that this is a valid avenue. And I think that's kind of where current research is. But this question is not going to go away, which is trying to understand what is actually happening. Why is it that neural networks that have a theta that's absolutely enormous, there's no reason by this theory of statistical learning that neural networks should work, and that's been observed, that observation has been made. It hasn't been observed in practice, of course. The observation in practice is that they do work. But this idea that they shouldn't work, based on this classical theory, is one that forces us to understand what's happening. Is it something like this? There's been other suggestions that it's properties of the optimization algorithm. So you're optimizing over a huge space, but perhaps your optimization algorithm only takes you to a subset of the space, which means that I only need to consider covering numbers of a fraction of the space. So what I'm trying to make connections between is the basically central question of the modern version of statistical machine learning, which is why do neural networks generalize? Or when do they generalize? And you're not going to have success, and no one has had success, though people have tried, by looking at the space of parameters of a neural network and trying to apply covering numbers. So these are interesting ideas that once were useful for algorithms like regression, like linear regression, which truly do the solution to a linear regression problem will truly consider all possibilities in the space. But neural networks must not be doing that, and I think a central question is why. We're not in a new era where these old results from statistical machine learning somehow don't apply. We're seeing that our way of understanding them and applying them to modern problems seems to be considerably incomplete. So I think this is a real challenge for people interested in theory, and seeing how are we going to bridge these ideas. So again, you know, the basic principles of empirical risk minimization, don't make any assumptions about the model that you're using. It's not that we somehow can move past it. We just, I think, don't yet understand the right tools for understanding how to apply those ideas to modern problems. And finally, let me say that I think that for again, to the students in the audience, there are really important connections, not only to this fundamental question of neural networks, of why do they generalize, but also just to tools that tools in probability, tools in geometry, tools in optimization and algorithms that are really important. And these are some of the areas that you should be studying if you're interested in these main theory challenges. I'm happy to answer any questions.
Thank you, Costa, for keeping to the time and having time for questions.
I'll be around too if you have more technical questions that aren't suitable for a general audience discussion.
On these penalty terms that you have, usually we see penalty terms that are having, I would say, a relatively simple form, right? And L1, L2 type of things. Is there a reason that the penalty terms are so simple, or is there some order of complexity that one can introduce on the penalty terms?
I think that's a good question. I needed to represent here regularization in some compact way. So we definitely could have, I think actually regularization is anything that forces us to have a different objective in addition to fitting the data as well as possible. So I think, for example, adding data that has, on purpose, that has some kind of noise. So data augmentation we can see as a regularization term. If you're actually adding stochastic noise to your data, that's probably very similar to adding an L2 regularization term. I think with the regularizers that we see, my guess is that they're mostly linked to, first of all, they're easy to implement, and they add to the convexity of the problem. So there are technical and computational and numerical reasons why I think that they've, like L2 regularization has appeared in many different fields of applied science. So my guess is that, you know, I can't really imagine that will have closed form terms of a regularization, of a regularizer, but on the other hand, implicitly we can think about having a neural network that's been pre-trained be also some kind of a regularizer as well, as long as it's serving this term of a penalty that is separate from what our training data are.
There are some techniques where people actually, they do it the other way around, but it doesn't matter. Instead of theta, they have equations that are describing the physics of the system that describes the data. This is a method originally developed in Greece, actually, by Isaac Lagaris and Likas back in the 80s. Now it's coming with the name PINS. And I wonder if you have any opinions about that.
So the equation, so you're penalizing deviation from satisfying those equations? Or
That's right. You penalize, you use a neural net to do Galerkin, and then you solve the equations using the neural net, and you add it as a penalty term to this minimization. Instead of solving the equations, you solve them through an optimization. And there's not very clear theory about that, especially when the data comes in. But anyway, maybe I'm asking too much.
There's one guy over there.
Hi, thank you for your presentation. In the last slide, you show us some fields that someone could research. You refer on high dimension statistics and geometry and optimization. Do you have some examples where, for example, a student nowadays could research on that field? So what do you mean by geometry in statistical machine learning, for example?
Yeah, you're asking for specific references.
What do you mean by that? I mean geometry.
Are you asking for references, or do you mean about this word geometry? And basically, there's interesting interaction between probability distributions in high-dimensional spheres, for example, behave completely differently than our intuition in 2 and 3 dimensions because of where that concentrates, and then that has an impact on optimization problems that because the data that feed these optimization problems are data driven, and so depending on, and they have an understanding their performance or understanding their behavior depends on properties of the data. So for example, some years ago it was really interesting to study problems that didn't have strong convexity properties but had only strong convexity in some limited directions, or even the space was non-convex, but because of the structure of the data and concentration inequalities that high-dimensional data satisfied, the optimization trajectories only followed paths that enjoyed this strong convexity. And those led directly into results about rates of convergence and basically the kind of results that we're interested in here, and generalization guarantees. So I don't know if to what degree that answers your question, but I can tell you I'm happy to send you or anybody my favorite references. These are vast areas, and there's been a huge amount that's been written about them, both for more classical models, but also attempts to bring this into the study of neural networks. I would say it's like one of the more active areas on the theory side of machine learning and neural networks.
Thank you.
Thank you. Other question?
Thank you. First of all, congrats on your presentation. I would like to ask, as a person that don't knows a lot about mathematics, I want to ask something basic, actually. What is that capital theta space? Is it the space of a numerical space?
So, okay, yeah, good. Thank you for asking that. So here's a simple example that I showed in the beginning maybe I'm looking for all rules that are formed by a straight line, and if you're on one side of the line, you're plus. If you're on the other side of the line, you're minus. In that case, capital theta would be 3 numbers, theta 1 and theta 2, and theta 0. And for all possible choices of those 3 numbers, you can describe all possible lines. And so the theta corresponds to all possible decision rules that I could make. But we can also think about it as theta corresponds to the thousands or millions or billions of parameters in a neural network as well.
Okay, so I see it like,
So it's numerical, yes, they're numbers.
okay, it seems kind of like the outcome. I mean,
And it is also, one of those thetas is going to be the outcome of my, sorry to scroll too much here. So I want to show this. So in this picture, I have data, I have a finite number of data, and I search through all possibilities here to find one point where if I plug in that point, it corresponds to a decision function that agrees with my data to the maximum degree possible. So my algorithm, my optimization algorithm, is looking in this space and finds one point and says, this is what I want, this is my decision rule. And the question that we want to answer is, okay, for that theta that I searched and found, I find that it has 85% accuracy. How much is that theta, how much accuracy is it going to have on future data? That's the central question.
okay, thank you a lot.
Costa, I think this is important for everybody to understand. Is it fair to say that each point is a trained neural network?
Each point we can think of as being a trained neural network.
Or,
Yes.
or one of the many lines that you can have in a linear
Or one of the one of the lines that we could have.
Does that help?
Yeah,
Um,
so it is the outcome of the procedure.
Other questions? Yes, the lady over there.
Hi. So it's not my area, machine learning, but I'm trying to learn more. So, but for years I hear on the street, let's say, people telling me that we don't know why deep learning works, no one knows. So it's been some years that I've been hearing this from people. So I would like to ask, has anything changed? Has any breakthrough occurred? And what is different in deep learning and in theory that makes it makes people say that we don't know anything? So what?
Okay, it's a long discussion, but the basic thing that I think is the most different is that maybe before the success of neural networks, we would never dare to make this too big, because everybody knew this classical theory that says, hey, if you have too rich a description, you're just going to overfit. If you're fitting very high dimensional polynomials to your line, you're going to overfit. If you're fitting a very deep tree, you're going to overfit. If you're boosting too many learners, you're going to overfit. And now in neural networks, we're seeing that explanation, that's not happening. So we're training models with way more parameters than data in some cases, and yet we're seeing that it succeeds. And I think that has put us into this. There's nothing on the theory that has changed. What that points to is that we don't quite yet understand what's happening. And these are and at the end I kind of drew some pictures of what some people have suggested. One idea is that the data that we have implicitly force us to implicitly lead us to only consider a small portion of this vast possible space of parameters. So that could be. It's well known that in any example that you have, you can create a neural network that agrees perfectly with the training data and is exactly opposite of future data. So we know that we can do this. But why is it that we never find that example when we actually train a neural network? We know it exists. There's no reason that our optimization procedure wouldn't find it, but somehow we don't. And that is one of the, I think, still something that is not well understood. Is it because of the data? Is it because of the particular way that we train neural networks in the optimization procedure? So I think that is what has changed, that we are using to great success neural networks that are extremely rich, that have this huge space theta, that if we don't understand anything more, we won't have an explanation of why they work, even though we can see that they do work.
Other questions?
Hello. My question is I got a bit confused about what is the purpose of this algorithm. Is it like to define like a loss function, or like to find the optimization of what? That's my question. That's where I got confused a bit.
So I give you data, and you train a neural network, and you find that it's 95% accurate on your data. But you don't care about that because you already had the labels for your data. What you care about is how accurate is it on the data you got tomorrow. Right? So if it's accurate on 95% of the data that I have today, I would like it to be accurate to some number that's close to 95. What is it that we need? How can we guarantee that? We haven't seen tomorrow's data. What is it that we need so that we can have that confidence? Of course, it relies on the process that generates tomorrow's data, but also it depends on what we did. So this is what statistical machine learning, that's the central question. How can we link future performance on future data, to performance on the data that we have?
Okay. There's one hand over there.
So if you have a neural network that, let's say, needs to recognize dog pictures, and you feed the neural network with very, very varied data. Let's say you want to recognize every breed of dog, then theta will be very large and it will overfit, if I understand correctly. And how do you optimize that?
So the theta is how big your neural network is. How many convolutional layers, how many channels did they have? Those are the basic parameters for that you have. So theta is very big if you have a very deep and a very wide neural network. And indeed, you might overfit. So the algorithmic question is, how shall we design and train a neural network to recognize dogs? And the mathematical question is, what do we need to guarantee that if it works on the data that you have, it will work on the dogs that you try to classify tomorrow, to recognize tomorrow?
Costa, if I can rephrase a bit this question, I think it's quite interesting, is what happens if the new data are very far, very different from the training data? Is there a way to still get something interesting theoretically?
Yeah, that's it's a great question, and there's a huge amount of work on looking at how much worse are we going to do if the distribution has changed. In many cases we find success, but yeah, I think that it's probably a long discussion to say something.
What I'm trying to say is that does the theory of VC dimension or anything help us in understanding that? Or?
Well, to be clear, I think that the theory of VC dimension has not yet helped us even in understanding why neural networks generalize at all, even in the IID setting. We wanted to, because it's one of the few ideas that we have, but I think it has not yet provided an explanation even in a simpler setting. But this is one of the key tools that we have, so it should be one of the ideas that we could try.
There's one person over there.
Hello there. I got a question about the regularization process in general. Actually, two questions. At first, it seems kind of arbitrary to me that just by adding a term lambda multiplied by theta, that we actually get to minimize the parameter space. How does it actually work? And the second question is that, how do we choose that lambda? Because I've seen in methods L1, L2, or LPLQ by Alessandro Buccini, that those methods are not always backed by mathematics. They're just backed by data, trained sets, and we just arbitrarily choose a parameter that satisfies what we want to achieve. How do we actually choose that parameter? Thank you.
So one way to think about overfitting is that you're fitting noise in the problem. And this regularization term is as opposed to fitting trends. If you have something else to worry about, like this regularization term, maybe intuitively you can't afford to fit noise anymore. You just have to fit the big trends. Maybe that's one way to think about it. Now, how you choose lambda, there are definitely mathematical principled ways for how you do it, but I think we don't have the link to very good and very usable mathematical models for where the data come from. So if you tell me that I have sub-Gaussian IID data, I'm not going to fit lambda using cross-validation. I'll fit lambda just using how the theory predicts, and it will do extremely well. So but in reality, data are much more complicated than we can really describe, and so we end up we use data to find a good lambda. So this is one of the hypertuning parameters, and there's many other approaches. You can do regularization by early stopping. You can do regularization by injecting noise into the problem. In neural networks, we have other techniques. You can use normalization inside the network. You can use dropout layers. You can use other things that are really trying to mess with your ability to fit the data, to fit every last detail of the data. So again, in spirit, regularization is an attempt to avoid fitting the noise and just try to fit the main trends that you can afford to fit. But I think doing it with data realistically is probably the best way to do it.
Okay, I think we'll have to stop here and go to the next talk. Thank you very much.
Okay, thanks for your attention.